Hey everybody, welcome back to Remote Physics. Today I want to talk about some angular momentum concepts, and I want to work through a classic physics example of a collision and how it affects the angular momentum of an object. So what we learned last week is that if you have any kind of rigid body rotating, we could find the angular momentum of that object L is equal to I omega. Don't ask me why it's L, just the way it is. Angular momentum is equal to the rotational inertia of that object multiplied by the angular velocity of that object. Notice I said angular velocity and not speed because this is a vector quantity. For angular momentum, it depends on which direction the thing is rotating in. And remember, this is the rotational analog for linear momentum. So, something I want to talk about today, that you could have an object with linear momentum, and depending on how you look at it, it could have angular momentum instead of linear momentum. What do I mean by that? Let's say we have like some kind of truck. Let's draw a truck over here. And it's going this way. Truck has some mass m going at some velocity v. Now we can all agree that this truck has linear momentum, right? Translational momentum. But what if we're standing over here and we're watching this truck go by? This is me pointing to the truck. Hey, look at that truck. If we're watching this truck go, according to my frame of reference, this truck could have some angular momentum, right? It depends on the frame of reference of how we're looking at it. From the frame of reference of this line or where the truck is, it's linear momentum, but if we change our frame of reference, now suddenly we're like the axis of rotation, and we could watch this truck go by and actually calculate the angular momentum from our position over here. On one of the videos that I had you watch last week, we saw that the angular momentum of any kind of point mass, if it's moving away from some reference point over here, we could say that that angular momentum is mvr sine theta. M is the mass of the truck, v is the speed at which the truck is moving, r is the distance away, and theta is the angle between our position vector and our velocity vector. I'm going to draw this a bit more generalized. Okay, so if we have like some rotational axis over here, and we're watching some point mass go by, the distance away we can call our, it's hard to draw straight lines, our position vector r. This mass has some velocity vector v. And we can say that the angular momentum is just like I wrote before. Angular momentum is rp, linear momentum, sine theta, which is the same thing I wrote before. Keep in mind that this theta here is if I extended our position vector, theta is this angle over here. Okay. Another way we could write this is r mvr sine theta. Another way we could look at this, like yes, we'll calculate the angular momentum at this position here, but r sine theta actually ends up being the point of closest approach, which is like if this mass comes up here, we can substitute that r sine theta for this distance here. You can call it like r prime. So we can look at the mass, the velocity, the distance away, and the sine of theta between it, or we can substitute r sine theta for just this distance here, which is the point of what we call closest approach. So you could also call this mvr prime. As long as you know this distance, you can just get rid of that sine theta. For a lot of our examples, the collision happens at the point of closest approach, so we don't have to worry about the sine theta at all, because here it's just like 90 degrees, it drops out. But again, this r sine theta is the same as that distance r there. Okay, quick little review of angular momentum of a object which seems to be linear momentum. Let's talk about our classic physics example, where we could analyze the conservation of momentum of the whole system and make some pretty cool predictions about what's going on. Okay. Here's our situation. We have some kind of rod with a fixed axis. We're going to call the mass of the rod capital M, and the length of the rod we'll just call R. And then we're going to have some object, some ball, with mass of little m coming in at some speed v. So here's the situation. This object is coming in, this rod is initially stationary, and this mass is going to collide with the rod. We're going to look at 3 different cases of this collision. The first case we're going to look at is when the ball comes in, strikes the rod, the ball comes to rest, and then the rod starts rotating. That'll be case 1. Case 2 is when the ball comes in, sticks to the rod, and then they both rotate together as a system. And then the third case we're going to look at is when the ball comes in, collides with the rod, and then the ball bounces back, and the rod is free to rotate in the other direction. We're going to look, our goal for all 3 cases is to compare the angular velocity of this rod after the collision. Okay, so here's case 1. So case 1, the ball is going to come to rest. So here's before the collision and after the collision. Like we talked about with our linear momentum examples, it's always a good idea to draw a diagram before and after so we can easily analyze what's going on with the system. This ball comes in, comes to rest, and then the rod will have some angular velocity omega. Again, this is a fixed axis. Before we dive into this case and analyze what's going on, let's just define some things about our system here. I'm going to solve this all out algebraically, and then we'll actually calculate some of the values. But we could give some of these quantities numbers. We could call the mass of the rod, we'll call it, let's say, 10 kilograms. We could call the mass of the ball, we'll say, what, 5 kilograms? You could say the length of the rod is 4 meters. And the incoming velocity, we'll say, is 8 meters per second. We're not really going to touch the numbers until after we solve this out algebraically, but these are the numbers we're going to be using to solve this system. Another thing to keep in mind, we need to know the rotational inertia of the rod. This is not something you guys need to know, but if you look it up, the rotational inertia of a rod that's could rotate about one end. We have one fixed axis is 1/3 mr squared. M being the mass of the rod, that's why I use capital M. R is the length of the rod, which we define to be little r, and that'll be squared. Okay, so let's dive into our first case where the mass comes to rest and the rod is free to rotate. Let's see how this affects our angular velocity of the rod. So for these kind of setups, we're going to be analyzing the angular momentum of the system. This is a situation where momentum is conserved, angular momentum is conserved, because there's no external torques acting on the system. So we can look at the conservation of angular momentum here. The angular momentum before the collision is going to be the same as the angular momentum after the collision, looking at the whole system. It's very important to identify what objects actually have angular momentum initially and what objects have angular momentum after the collision, and make sure we set up our angular momentum expressions in the correct way. All right, so before the collision, looking at the left side, the rod is at rest, so it can't have any angular momentum. But this ball coming in does have angular momentum from the frame of reference of this axis here. And we want to analyze what's going on just before the collision and just after the collision. So when this ball comes in, it's at that point of closest approach when it collides with the rod. We can make that assumption. So our initial angular momentum of the system is just the angular momentum of this object when it's close to the rod. And that's going to be M, V, R. Again, that R is the distance of closest approach. When it's here, you don't have to worry about any kind of sine thetas or anything like that. Another way to look at it is when it's right here at the rod, sine of theta is just 90 degrees, so it drops out. Okay, now we don't have to worry about the angular momentum of the rod. All of the angular momentum initially is manifested here in the ball. And then the ball collides with the rod, and then the rod is free to rotate about its axis, and the ball comes to rest. So on the right side of our equal sign, this is the final angular momentum of the system. Only the rod has angular momentum here. And when we have a rigid body rotating, instead of looking at the point mass expression, we're going to be looking at our rigid body expression, I omega. I being the rotational inertia of the rod, omega being our angular velocity of the rod. Calling it positive because it's rotating counterclockwise about its axis. And here we can now start plugging in what we know and see if we can solve for this angular velocity omega. Little m is the mass of the ball, speed is given, r is given, but this I for the rod along a fixed axis, we have an expression for it. It's 1/3 mr squared, so we're going to plug that in. mvr is equal to 1/3 mr squared multiplied by omega. All right, so let's solve for this omega. Moving the third over, dividing through, we'll see that we have an expression of 3VR. Make sure you can work out this algebra on your own, and make sure your paper is a lot less flimsy than mine is. 3VR, 3mvr all over mr squared. If you were clever initially, you would have saw that one of these r's go away. It's equal to omega. So we have a final expression of 3mv over capital MR. And that's our expression for omega. Remember this expression because we're going to compare the angular velocities for all three cases. We're going to see which one is the greatest, which one has the least. And we're actually going to calculate out some of the numbers based on the given information. But remember, this is generalized, so it doesn't matter what the information is for our system. This expression always holds when we have a rod fixed along an axis on one end, and we have a ball coming in with some velocity colliding with it. All right, based on our given information, plug it in yourself to make sure you can do it and also to check my work. But when I calculated this initially, when I calculated myself, I got an omega of 3 radians per second. Okay, based on this system and the given information, when that ball collides, that rod is going to rotate at 3 radians per second. It's always important to know what this really means when it's rotating like this. 3 radians is about 180 degrees. So in 1 second, this rod is basically going to be swinging over to the other side. I'm writing on my wall. Okay. All right, so that's case 1. I'm going to take this expression and write it up in the corner, and we're going to compare as we go for all 3 cases of this system. All right, pause the video, write down what you gotta, and I'm going to start erasing. Okay. That I'm going to write over here for case 1. Yeah, 3. Look how organized I am. Boom. I'll hold on to that. Gonna erase this. Now let's look at case 2. For all 3 cases, the initial setup is going to be the same. Rod at rest, ball's coming in. But for case 2, what's going to happen is the ball is actually going to stick to the rod, and now the rod and the ball are going to rotate all together. So now, for after the collision, we have our rod with our object now fixed to the other end, and this all together is going to have some angular velocity. How is this going to compare to the first one? Make a prediction. Do you think it's going to be quicker? Do you think it's going to be slower? Based on what you understand about linear momentum, you should be able to have some kind of idea of what's going on here. Based on what you know about rotational inertia, you should have some idea of what's going on here. But it's always good to work it out and see what's going on. All right. So, now that the ball's stuck to the rod and they can rotate together, again, we're going to analyze the angular momentum, the conservation. There's no external torques acting on the system in all 3 cases, so conservation of angular momentum is going to hold. Okay, so the initial angular momentum doesn't change. That's just going to be mvr. But now, the final angular momentum of the system, we want to look at all of our objects within the system. There's a few different ways to look at this, 2 different ways to look at this, but either way you're going to get to the same answer. We can take a look and say, well, the rod's rotating and the ball's rotating, and they have the same angular angular velocity. So we could say that we have I omega of our rod. So we'll call this I rod. But now that we have this point mass no longer moving linearly, but actually rotating about, we can look at the rotational inertia for a point mass going around. And the same angular velocity, because it can be rotating at the same rate when it comes to the angle measure. If you recall, the rotational inertia for a point mass about some axis mass is equal to, you add up all the point masses that are going around, the sum of mr squared, but here it's one point mass going around, so it's just little m, r squared. All right, so we can factor out the omegas. We could say mvr is equal to I of the rod plus I of the point mass, all multiplied by omega. And with this, we actually arrived at another way that we can look at this system. We didn't really talk about this in class, but when it comes to rotational inertias of multiple things, maybe a rigid body, a point mass, maybe another rigid body as well, as long as they're rotating about the same axis, we can add the rotational inertias of each one, the rotational inertia of the rod and the rotational inertia of the point mass. Here's the rotational inertia of the system now, and it's all multiplied by omega. Either way, you're going to get to that result, though. All right, our goal here is to solve for omega, compare it to case 1, and see what changes when the ball actually sticks to the rod. All right, let's do it. So we're going to plug in what we know about the rotational inertia of the rod and the rotational inertia of the point mass. We have mvr is equal to I of the rod is 1/3 big M r squared plus no constant of 1 out in front, so this is little m r squared, all multiplied by omega. Okay, here we want to simplify, solve for omega. On the AP exam, they don't expect you to simplify, but for these kind of situations, it's good to get this in simplest form so we can easily compare it to our the angular velocity of the first case, and we can compare and see how it changes here. What I'm going to do is I'll pull out an r squared, and then I'm going to divide everything over. So we'll have mvr all over 1/3 capital M plus little m multiplied by r squared. And again, one of our r's go away. So we get mv all over 1/3 big M plus little m multiplied by r. And this is going to be equal to our new omega of the system. Now before you plug in numbers and actually solve this out, compare this omega to our omega from case 1. For case 1 it was 3mv over capital MR. Here now we lost the factor of 3 in the numerator and our denominator expanded. It's not just m times r, it's a sum of these masses multiplied by r. So you should be able to see that this omega is going to be less than the original. We decrease the numerator. Yes, we decrease this mass, but we're adding this little mass and still multiplying it by r. This is going to decrease the total angular velocity. And if you work it out with our numbers, you would see that this angular velocity, omega, is 1.2 radians per second. Less than our original. Again, picture what this means. What does 1.2 radians per second mean when we have an object rotating? Well, 1 radian is about 60 degrees, so this is going to be rotating a bit over 60 degrees every second. It's not going to go all the way over to the other side like the original case was. All right, that's case 2. Now I want to look at case 3, where the ball comes in and actually collides and bounces back. And how is that going to affect the angular momentum of our rod situation? Pause the video, take a picture, write down your notes, whatever you got to do. I'm going to start erasing. I'm going to take this omega, put it up here so we can compare, and then we're going to look at case 3. Boom, boom, boom. Most exciting part of the video, watching me erase and organize. This is going to be case 3. Case 2, we saw that it was mv over 1/3 m, big M, plus little m, multiplied by r. Also make a 1, make a 2, this is equal to 1.2 radians per second. Boom. All organized. Probably could have told you to just skip ahead to this part. Videos are weird. All right. Now, for this next case, case 3. What happens is the ball collides with the rod. The rod rotates with some angular velocity, omega, but now the ball bounces back with some new velocity. We're going to call this our initial velocity. We're going to bounce back at some final velocity. Let's call this final velocity 2 meters per second. But it doesn't matter what our numbers are. We're still going to solve this out generally and see how the expressions compare, and we'll see if we can solve for that omega. Okay. Case 3, again, angular momentum is conserved. The initial angular momentum of the system is going to be equal to the final angular momentum. Okay. Tell you what, I just made a decision here. I want you to solve out this example based on what we, based on how we did the first 2 cases. I want you to solve it out, get me the expression, compare it to the other 2, and actually calculate the new angular velocity of this rod. Make a prediction. Is it going to be quicker than case 1, slower than case 1? How's it going to compare to case 2? And I want you to actually calculate the numeric answer based on this given information. This is something you could do if you look back on case 1 and case 2. There you go. You can do it yourself. All right. So That's the example I wanted to work out with you for conservation momentum. Over the rest of the time this week, I might post more videos doing maybe conservation of angular momentum examples, maybe some more torque examples. You guys let me know what you need. You know the quest is going to be due on Thursday. If you want to see me work out any of those problems, or if you want to see any other particular concepts or problems, I'm here for you. Anything you need. Thanks for tuning in. Work out case 3, that's going to be your assignment. I just decided, and I'll see you guys soon.